Hi. Okay, let's start this again and start talking about the Beer-Lampert absorption law. We've actually already done this, of course, and that is the idea that the absorbance is equal to a linear function of the molar absorptivity times the path length times the concentration. And at least within the dynamic range, you end up with a nice straight line relationship between absorbance and concentration. As opposed to, remember that absorbance is the inverse of percent transmission, which is a logarithmic function. So when we're doing concentration, we normally don't do percent transmission versus concentration because the absorbance versus concentration gives us this nice straight line. Just as a reminder, the way we got that is we looked at absorbance versus wavelength, and we picked the wavelength that gave us maximum absorbance. That's of course called lambda max. This is the wavelength where the molar absorptivity is going to be the highest and therefore the highest sensitivity. Remember, so if A is equal to M times C, the slope is the sensitivity. Now we've all done this, and we've talked about things like sensitivity and analytical sensitivity, limits to detection, and of course the dynamic range is where the Beer-Lampert law holds up. The question becomes, what if we have a solution that has more than one species? How much light is going to be absorbed by multiple absorbers? Fortunately, this is a pretty straightforward and easy problem. What we look at is that if this light goes through, we're wondering, well, what is the probability of A, the photon interacting with one of those molecules, bumping into it, and B, what is the probability that that molecule is actually going to absorb that photon? If we neglected like all the red molecules in here for a minute, and we only worried about the blue ones, then what's the probability of those blue molecules absorbing one of these photons? Well, that's just the Beer-Lampert law. Times the path length times the concentration of the blue species. And if we thought about just the red one, then the absorbance of the red one would just be the molar absorptivity of the red one times the path length times the concentration of the red one. Remembering that these are wavelength dependent. So maybe the red one has a lambda max, and I don't know, let's just make something up here. Say 500. And the blue one has a lambda max, and let's say 600. Notice this is this is going to look blue to us because it's absorbing, kind of in the red, and this one's going to look red to us because it's mostly absorbing in the blue. So if we put a photon through here, it sort of depends on which wavelength we're putting through. If we put in a 550 photon, it may be absorbed by the blue and by the red. In that case, the Beer-Lampert law suggests that the absorbance of a light, any wavelength, going through here is simply going to be is going to be equal to the molar absorptivity of the blue at that wavelength times the path length times the concentration of the blue plus the molar absorptivity of the red at that wavelength times the concentration of the red. Bottom line of all this is the total absorbance in a solution really is equal to just the sum of the absorbance of the blue plus the absorbance of the red. That is the total concept of the Beer-Lampert law.